So in example 3, part E, we have f of x equals the natural log of quantity x squared minus 9 on the closed interval from -2 to 5. So first we want to check to see if our function is continuous on this interval, and the natural log immediately raises a red flag because remember, you cannot take the logarithm of 0, nor can you take the log of a negative number. And so you can graph this function, or you can solve the inequality, but I would need an absolute value of x that is greater than 3 in order for this function to be defined. And so what that means is that the extreme value theorem does not apply, since f of x is undefined for all x values between -3 and +3 inclusive. And since this interval overlaps with this interval, we can make the argument, therefore, f of x is not continuous on -2, 5. Another way to think about this is to just identify the domain of this particular function. And so the domain of f is going to be equal to -infinity to -3, not included, union 3 to infinity. So we can't do it. This is why it's so important to always check that continuity criterion on the interval before you get started. All right, let's take a look at f. So in f we have h of x equals the cube root of x minus 2 quantity squared, and big sigh of relief, that's an odd root, so we're not going to have any issues with imaginary numbers or anything like that. So h of x is continuous on 110, since the cube root of x is everywhere continuous. So let's rewrite h of x using rational exponents, and that will give us x minus 2 quantity to the 2/3 power, and that will allow me to take the first derivative using the power rule. So h prime of x is going to be 2/3, so 2 over 3. And then remember, it's power times base down 1, and so 2/3 minus 1 is 2/3 minus 3/3, and so that gives me a -1/3. And so let me go ahead and write that in the denominator so I can make it positive. That's x minus 2 to the +1/3, and we will set this equal to 0. Okay, but there's a problem. What value of x could ever make this equal to 0? So imagine x is a negative number. So we can take the cube root of a negative number and we get a real number that is not equal to 0. Imagine x is positive. Again, we take the cube root of a positive number and we end up with a real number for h prime of x. Again, not equal to 0. Well, what if x is equal to what if x is equal to -2? So in this case, I end up with a point that is, it makes h prime of x undefined. So that means that I will have a critical value at 2. So h prime of x is actually not equal to 0 for any value of x, and furthermore, h prime of x does not exist at x equals 2. So remember, the definition of our critical values was where the derivative equals 0 or does not exist. So that means 2 is going to be a critical value. So we jump back into our candidates test. X 1, 2, and 10. So the endpoints and the critical value. So f of x, and let's see, for 1 we get 1, For 2 we get 0, and for 10 we get 4. Now remember, where did the 0 come from? Well, we're plugging back into the original function. And I wrote f of x. I should have written h of x because that's actually my function. Alright, so h of x is what we're plugging into, and when we plug in 2, we get the cube root of 0, which is 0. And so we can find from our table that the minimum value is going to be 0, and the maximum value is going to be 4. And that concludes our investigation of the extreme value theorem.